Great. So we are recording the lecture now. So this is lecture number 9. We will continue our discussion from yesterday, where we are talking about the parabolic equation, that is the infinite slab problem. So we had talked about the governing difference equation. So I had shown you the explicit form of that. And now what we will do is we will also talk about the boundary conditions, because we didn't talk about that yesterday. So let's quickly rewrite the governing difference equation first. So we had used a forward difference in time for the time derivative, and on the right hand side we had used a center difference in space. Okay. So this scheme we had called the forward time center space scheme, because for time derivative it's forward difference, and for space derivative it is center difference. Okay. So now if we write it in the form of unknowns on the left hand side and knowns on the right hand side, so what we get is theta n plus 1 I on the left hand side, because that is the only unknown here. If I draw the stencil of the scheme, okay, so this one is the I comma n, and we are writing n plus 1 comma I in terms of I comma n, I minus 1 comma n, and I plus 1 comma n. So that gives us this kind of a stencil for the scheme. Right. So this is the update formula for finding theta n plus 1 at a given position I. So for which values of I do we apply it? We apply it for I equals 1 all the way to I equals n minus 1. So all the interior points. But boundaries is something we haven't talked yet. So we apply this update formula for I greater than equal to 1 and less than equal to n minus 1. Remember, I equal to 0 is our left boundary, as I have shown in the figure, and I equal to n is the right boundary, the index for the right boundary. So let's look at our boundary conditions. So let's look at the left boundary. For the left boundary, we had said that it's a center plane of the infinite slab. So here we have del theta by del x equals 0. So this was the differential form of the boundary condition on the left boundary. So can anyone help me how I can discretize this? What sort of difference form can I use corresponding to this? Forward difference, yes, it's the left boundary, so I can take a right point. So this can be discretized as theta at, so theta at this boundary, this point minus theta at this point, sorry, not this one. So the blue squares, theta at I plus 1, which is I is 0 here, so I is equal to, so theta at 1 minus theta at 0 upon delta x is equal to 0. But should I apply it for n plus 1th time or nth time? N plus 1th time, because nth is already known. So this time marching that we are doing, this time stepping that we are doing is something that's being done for the situation where nth values are already known. We are calculating the n plus 1th values here, right? So it makes sense to write this for the n plus 1th time. Okay, so update formula had a total of n minus 1 equations. Now we have one more equation. Now let's do the boundary condition on the left hand side. Sorry, right hand side. On the right hand side, the boundary condition that we had was that the conduction flux is equal to the convection flux. So it was the Robin condition. So again, it's being done for the n plus 1th time, because nth time values for all thetas, including the boundaries, are known to us. So you can see that all the thetas, unknown thetas, theta f is already known. So all the unknown thetas are written at the n plus 1th time, and the derivative uses a backward difference, because we do not know and we have no information about what's happening to the right of the boundary. We only have information about what's happening to the left of the boundary. So it's theta at the nth spatial index, capital N, minus theta at capital N minus 1 upon delta x is how we discretize the derivative at the right boundary. For the theta value, which is simply theta at capital N plus 1. So it's common to write the unknown terms on the left hand side and known on the right hand side. So we combine this and we can explicitly now write theta at, sorry, there's no n plus 1, I'm sorry, this is n. Capital N is the last index. So theta at capital N point at the n plus 1th time can be written explicitly in terms of all known values, simply some algebra. So you can see that let's revisit the boundary conditions now. Let's look at them, both of them. So for the left boundary condition, it helps us to specify theta naught at the n plus 1th time, right? So I can actually write this as theta naught is equal to theta 1. So there is an order to which we will visit the points at the n plus 1th time. First we do the interior points, because you can see that both the boundary conditions require information about one of the interior points at the n plus 1th time. For instance, this one, the blue circle, theta at small n plus 1th time at the index number 1. Now that is only known once you have visited the update formula for I equal to 1. If you have not visited that, you have not calculated theta 1 at n plus 1th time. Okay. So first you have to do the interior points, only then you can do the boundary points. Otherwise, you will not be able to do the boundary points. So when you write the loops, you have to have an order. Similarly, for the right boundary, you need theta at capital N minus 1 at the small n plus 1th time, and that is only known once you have run the update formula for I equals capital N minus 1. Only then you can calculate the right boundary or run the right boundary condition. Is that clear? So I made a note that you have to update the interior points first. Well, not all of them, but just at least these two of them. So let's talk about the truncation error for the forward time center space scheme. So truncation error was because now you see that while converting the differential equation to the difference equation, what we are doing is we are approximating the derivatives, and because of that approximation we get some error. So we truncate the Taylor series to only one term. So we do not take the second derivative onwards there, so that results in error. So for forward difference, you remember the error was order delta x, and for center difference it was delta x squared. So this time in time it is forward difference. So we get an error which is of the order of delta t, because delta t is discretization interval in the time direction. So there has to be an error associated with the size of delta t you take. So it's order delta t because you have taken a forward difference in time, and for space it is still delta x squared because we have taken a center difference. So the overall error we get is truncation error is of the order of delta t comma delta x squared. So later in this course we will have a lecture on modified equation where we will actually see in detail how the error looks in terms of these delta t's and delta x. But for now I think it's quite intuitive because we have combined two different schemes, and each scheme's error we had talked about. So it's a combination of the two. Now we saw that the truncation error for the discretization method that we have used here, forward time center space, is order delta t and delta x squared. But what happens is when I solve the problem, the solution is actually order delta t delta x. Does anyone have any guesses as to why is this happening? Even though the discretization is of the order of delta t comma delta x squared, but the solution that we get is of the order of delta t comma delta x, not delta x squared. So it's inferior to the accuracy as we get in terms of the discretization method. There's a difference, right? One is our discretization method that we have used, one is the actual solution we get. So if you take the error versus delta x or delta t size, this is what you get. Could we guess? So the overall solution is a combination of the governing difference equation plus boundary conditions plus initial condition. Now for the governing difference equation, we have used a scheme which is order delta t comma delta x squared. What about boundary condition? What sort of error does the boundary condition have? First order in space, it's order delta x. Initial condition is exact. We have already specified the exact value, so there is no error associated with this. So what we see is that even though we spend a lot of energy in making the discretization of the differential equation as order delta t delta x squared, but we did not get that squared benefit because our boundary conditions were delta x. So the overall solution takes the behavior or takes the lower order out of these three, the lowest one. So delta t had a lowest order of delta t and delta x had a lowest order of delta x here because of the boundary condition. So the natural question is then what can we do to get higher order schemes, because higher order schemes are quite useful, as we will again see later, especially in the, we will discuss this in the lab, this idea. So what we can do is there are ways to get second order boundary conditions. So that will be discussed through the lab. Okay. So in lab I will give you a problem, I will tell you how to implement that and you can implement and see for yourself that indeed you get better accuracy of the overall solution if you use second order boundary conditions. It's a very important idea because see ultimately it's the overall solution's accuracy that matters. So it's actually quite important to spend that extra energy in making the boundary conditions second order, otherwise there is no point doing second order for all the interior points. Solution takes the behavior of the boundary conditions, I mean lower one of the two. Okay, any questions? So this was the explicit scheme and it was called explicit because if you look at the update formula for our interior points, we can see that we are explicitly calculating the value of the unknown theta n plus 1 at any given I in terms of all the known values. So that is explicit representation. So now what we will do is we will talk about implicit, or before that let us write the algorithm of this scheme. So first we initialize or declare variables. So we have to initialize delta t, delta x, alpha. So these are alpha is a parameter in the equation depending on physical parameters. So we have to specify that, and delta t and delta x are chosen by the user. So depending on what sort of accuracy you need, what sort of computing time you require, so you will specify delta t and delta x values. So it's a lot of experience that goes behind these, but they'll be, I mean, I'll suggest you some standard values to use in your lab, and then you can play around with the values by increasing or decreasing those. And then we have to specify theta old and theta new. Now you may be guessing what is theta old and theta new. So remember that we are calculating, we are using a time marching scheme or time stepping scheme. So using the previous unknown values, you calculate the previous known values, that is theta at the nth time, you calculate theta at the n plus 1th time, that is the unknown value. Now after that, you don't need to store theta at all times. You can do it, but that's a lot of storage. So if your delta t was such that your number of time intervals was 10,000, so you are storing 10,000 arrays of values which you may not require. Typically what happens is we require theta at certain times. So in the program what we do is we already know what times that there are, so we only store the latest time values, and as soon as our loop reaches that time where we need it, we copy that into a file. So rather than storing all the 10,000 theta values or 10,000 time interval theta values, you only store those discrete values where you need them. See, we need to do time stepping. We cannot jump from one to the middle. We have to go through all the time steps, but we don't need to store all the intermediate time steps. That's the idea. Okay. So at any time we are storing theta values, or we are storing theta values where we need to calculate them, and we have the information about the previous time. So we call theta new as the one that is unknown, n plus 1th time, and theta old as theta at the nth time. Okay, that helps us save a lot of storage power, and then all that storage has to be stored in the RAM, so that also decreases the RAM requirement for the solution. So then we initialize all the theta i's. So that's the old. To start with, we have some information about the initial theta. That's what we call the old theta I for all, including the boundary, because initial condition is known for all points, interior and boundary. Next, we use the update formula to calculate theta i's for all the interior points, as we discussed. Okay. So this is theta I new now, because old is already known, so we calculate the new values now. Now we will do the boundary conditions. Now we do the boundary condition, and then after that we will say that theta old. So now we copy the theta new values into the theta old values, because now we have to repeat the steps. So now that we have calculated all the theta new values, we will copy the theta new into the theta old. So our theta old gets updated, and now we'll move on. And this is something we do for all I values. And then we say n equals n plus 1. So in computing, when you say n equals n plus 1, it evaluates the value of right hand side and puts into the left hand side. So n was 0 to start with, so n plus 1 becomes 1. So the new value of n becomes 1, and then we go back to step number 3. That is, we now update or we calculate new theta values for all interior points. We do the boundary points for theta new, and then we keep repeating this until some stopping criteria is met. So stopping criteria typically would be that you have reached your final time. So you would want to run it for a maximum time, right? So usually we run it for till the time we need the information, or sometimes we run it until the solution stops changing. That's called steady state. So this is an unsteady problem. But if you run it for a very long time, what will happen is there will be a time after which solution will stop changing. So that will actually give us a solution for the problem which is del 2 theta by del x2 equals 0. Ultimately, it will reach a solution to this problem, because the actual problem that you had was del theta by del t minus alpha times this is equal to 0. But if you run for a very long time and solution stops changing with time, that means your del theta by del time is already 0 now. So the unsteadiness, for example, it looks like this, it's changing with time, theta at some I value, and then you see that after some time it becomes flat. So beyond this particular time, you have reached steady state. And you will see that in infinite slab, if you dip it in the fluid, fluid of theta f temperature, where theta f is not changing, after some time you will see that the whole slab will be at theta f, right? So depending on what criteria, where your interest lies, you will run it till that time. Questions? No, small n, time. Capital N, you cannot have special equality. I mean, boundary condition is such, but here what we mean is that you are moving to the next time step. Your small n will now become 1, then it will become 2, then it will be 3. So you are moving up. So this algorithm will help you write your computer program. When I give that as an exercise in the lab, you should be able to write them. By the way, I hope you are practicing lab 2 now. So lab 2 will be held on Thursday, that is day after tomorrow. Okay? So please make sure you practice it. Although I'll give you a solution, but it is best. So this time what I'll do is, since the solution is a bit longer than what we did last time, so rather than asking you to write everything in the lab, I will have some commented sections in the program. So the first case I will give you the complete program. In the second case I will have some commented sections. So some sections will already be filled, and some of those are sections you will have to fill. And that's very typical of testing your programming skills. So for example, we will break this into like you have algorithm. So rather than asking you to update interior boundary and everything, I will give you interior points update, but for the boundary I will leave a section. So update boundary condition 1 here as a comment, and below that you have to write the program for the boundary condition 1. Okay, and in the exam also you can expect something like that. So I will not expect you to write the whole program, or I will give you a program, I will say what is the error in the program. That's something I can check in the exams, right? So if you understand the labs, you will read the code, some section of the code, like this is the code for the infinite slab problem, which is parabolic 1D in space. There is an error in the block for boundary condition 1. Can you identify the error and correct it? Make sense? Okay. So please make sure you try to do the labs yourself, whatever you can, and then if you cannot write the complete program, you can write some sort of an algorithm, and then during the lab you can update your understanding. And if I also expect that after the lab, whatever you did not understand in the lab or whatever you could not complete in the lab, you do it after the lab. So make sure that by the end of the week you are clear about everything from the programming side. Right, the next one is implicit schemes. It's natural to have an implicit scheme given that we have an explicit scheme as well. So the first one we'll talk about is backward time center space. So earlier we are writing the equation around the point I comma n. This time actually what we do is we write it around I comma n plus 1, and you will see why, only then it makes sense. So when I discretize the derivative, the time derivative in a backward sense, since we are writing the derivative at I comma n plus 1, so del theta by del t becomes theta at the point at which we are writing it, and then one backward point which is theta at n. Okay, so this is the backward difference for time derivative. On the right hand side, we are discretizing center space at the point I comma n plus 1. So this is our governing difference equation. So now you can see that it's not explicit. I cannot evaluate the value at a given point using known values. It's an equation which has multiple unknowns in it. It's a linear equation. Let's draw the stencil of the scheme as well. So this is the point where we are discretizing, but we also get a left and a right point, and then the known value that is used is just one known value at the I comma n. So the stencil actually is sort of inversion of the stencil we got for forward time center space. So this is the stencil for backward time center space. So we have a total of n minus 1 simultaneous equations, that is coupled linear equations, and then we have 2 boundary conditions. So that gives us a total of n plus 1 simultaneous equations. So what I mean by simultaneous is that you have a linear system. So the first one is boundary condition, and post that, and again this time also I have used first order boundary condition like last time. So boundary conditions are same as last time, except that we have to solve them with the differential difference equation for interior points in a linear system. So we get a linear system. Again you can see it's tri-diagonal like the one we had for elliptic 1D equation. So you can use the tri-diagonal matrix algorithm to solve this. So the only difference between this and the elliptic solver that we had was that this time we have to solve the tri-diagonal system multiple times. So we solve it once to calculate the next time step or the unknown theta values. So once you do that, you have to repeat the step to calculate the next time step and so on. So every time step calculation requires you solving the TDMA once. So you can see it's a bit hectic than using an explicit scheme where you could simply write one explicit formula and run it in a loop for all I values. But here you have to take the inverse of the matrix, say this matrix. Or you have to use the TDMA algorithm, which is Gaussian elimination for tri-diagonal matrix system. So let's write the algorithm. So just try to identify where it starts differing from the explicit scheme. So first you initialize all the parameters as in the explicit scheme. Then we initialize using the initial condition, that is at n equal to 0 for all points including boundary points. I am not writing that explicitly, but it's the same as previous case. So next we solve the tri-diagonal system to get theta new values for all I points at n plus 1th time step. All I points, because when you write the linear system, it includes the boundary conditions as well. We just wrote that we have a total of n plus 1 simultaneous equations. So that means you are solving for n plus 1 unknowns, which is theta values at all points including boundary points. Okay, so we solve the tri-diagonal system to get all the theta values, and then the final step is now we have to copy the theta new values into the theta old values and then modify the value of n to n plus 1, and then we keep repeating that until a stopping criteria is met. Is that clear? I am moving a little fast because no, these ideas are already discussed. We are just discussing the delta differences between explicit and implicit schemes. Again, truncation error is the same order as forward time center space, because backward time is also first order in space, first order in time. So we get the truncation error as order delta t comma delta x squared. same as FTCS. Now, a very natural question would be, can we have a scheme which is order delta t squared? I am sure many of you are thinking that, because if higher order schemes are good, then how can we get an order delta t squared scheme? Yes, we can get it, and in fact we tend to use that scheme much more than using this scheme. So that's also an implicit scheme. That's the reason it comes under the discussion of implicit schemes. So it's called the Crank-Nicolson scheme, or typically known as the CN scheme. And you will see your software and open source codes, they will have this Crank-Nicolson or CN scheme written in the options that you have. So it's basically an average of explicit and implicit schemes. That is well, I should say it's an average of, because you can have different kinds of explicit and implicit schemes. It's an average of FTCS and BTCS. So if you remember the forms that we had, so this is the explicit scheme, and this is the implicit or the backward time center space scheme. So now if you look at this overall scheme, what you see is that we have 3 unknowns and we have 3 knowns. So the stencil actually looks a bit different from the other 2 schemes that we have discussed. It's sort of a combination of all the, so it has all the 6 points. So theta n plus 1 at I minus 1, I and I plus 1, which go on the left hand side if I rearrange the equation, and theta n at I minus 1, I and I plus 1, which go on the right hand side, plus some any constant terms as well. So this is the stencil of the Crank-Nicolson scheme. Before I close, just one more minute on a general scheme. So many solvers will give you an eta scheme. Some call it the theta scheme as well, but theta is a variable that we are using for temperature here, so I will call it an eta scheme. So eta in this case is a parameter which varies between 0 and 1, so it's like a dialer that you can tune as to wherever you want to keep it. And the equation that we have is written in the form of this. So del theta by del t is a function, some function of theta. In our case, this function of theta is alpha times del 2 theta by del x2, but it could be anything. So this eta scheme is used for equations, transient equations of this sort. So we write it as, the time derivative looks very similar. On the right hand side, we take a linear combination of f evaluated explicitly and implicitly. Now I can easily see that if I make eta equal to 0, what scheme do I get? Explicit? If I make eta equal to 0, what happens is that I only get 1 times f at the function evaluated at theta n. So you can see that I can write this unknown explicitly in terms of all the known values. That's called an explicit evaluation. Okay. If our eta is equal to 1, then what do we get? Implicit. Actually, we call it fully implicit. Fully in the sense that there is no contribution of the explicit terms. Implicit basically is a word which is used for situations where you are not using it's everything that is not explicit is implicit. But fully implicit means that there is no other explicit term. And if theta is half, what do you get? The Crank-Nicolson scheme, CN scheme. And actually what you do is in software or computer codes, what we have is we have to specify a value of eta. Rather than saying it is explicit, implicit, Crank-Nicolson and so on, you just specify a value of eta. They will have a help section saying that for explicit use eta equal to 0, implicit eta equal to 1, Crank-Nicolson eta equal to half, but you could use eta equal to 0.25. Okay, and these are ideas which we will discuss later as to why and how we decide which one to use. So there is a lot of art associated with deciding these numerical parameter values, and this only comes with experience as well as understanding of what they actually mean through this course, through courses like this. Okay, so we will stop here now. This is the end of implicit schemes. I will meet you on Thursday in the PC lab downstairs. I will send you an email with details of the lab. The lab is already uploaded on Moodle. Please try it. Yes, sir. For the governing difference equation. So this is for, thanks for pointing out, this is for GD only. Okay, so these schemes that we have, forward time center space, backward time center space, these are only for the interior point. So this is for the scheme. I should have specified that. Thank you.